Welcome to the session on failure mode effect analysis. The agenda of this session is 1. To understand the use of failure modes and effect analysis, FMEA. 2. To learn the steps to developing FMEA. 3. To summarize the different types of FMEA. And 4. To learn how to link the FMEA to other process tools. FMEA is an engineering reliability tool that helps define, identify, prioritize, and eliminate potential failures of the system, design, or manufacturing process before they reach the customers. Preventive costs to identify potential defects by FMEs are relatively low compared to in-house detection and correction of defects, and even much lower than recovery costs in case defects are found by the customers. It was initially developed by the US military in the late 1940s and early 1950s as a method to evaluate the reliability of systems and equipment. The methodology gained prominence in the 1960s and 1970s as other industries, including automotive and manufacturing, began adopting it to improve product quality and reliability. Today, it is widely recognized as a fundamental tool for identifying and mitigating potential failure modes in processes, products, and systems across diverse industries, including manufacturing, healthcare, telecommunications, and more. Types of FMEAs includes 1. System FME or Concept FME, also called SFME or CFMEA. A system is an organized set of parts or subsystems to accomplish one or more functions. System FMEAs are typically very early, before specific hardware has been determined. 2. Design FME, also called DFMEA. Design or part is a unit of physical hardware that is considered a single replaceable part with respect to repair. Design FMEAs are typically done later in the development process when specific hardware has been determined. And 3. Process FME, also called PFMEA. Process is a sequence of tasks that is organized to produce a product or provide a service. A process FME can involve fabrication, assembly, transactions, or services. The number of members in a FME team can vary depending on the complexity of the system or process being analyzed, as well as the organization's preferences. However, a typical FME team may consist of around 4 to 6 core members. Those are individuals who possess deep knowledge about the system, product, or process being analyzed. These cross-functional representatives offer diverse perspectives and ensure that all relevant aspects are considered during the analysis. They must possess honest communication, active participation, positive attitude, respects other opinions, and participates in team decisions during the analysis. Champion or sponsor, usually from top management, provides resources and support, attends some meetings, promotes team efforts, shares authority with team, and implements recommendations. Recorder documenter, this role is responsible for documenting the entire FME process, including meeting minutes, analysis results, action items, and any other relevant information. Clear documentation is crucial for maintaining a record of decisions made and tracking progress over time. Team leader, there needs to be a designated individual with good leadership skills, respected and relaxed, leads but doesn't dominate, maintains full team participation. This team leader may be a senior manager, engineering lead, or another appropriate authority within the organization. Facilitator, this individual leads the FME process, guiding the team through each step, facilitating discussions, and ensuring that the analysis stays on track. The facilitator often has expertise in FME methodologies and may also have project management skills to keep the process efficient. FME begins with understanding your customer needs, for which quality function deployment (QFD) is used. Develop and evaluate product process concepts. This can be done using brainstorming technique. Create an effective FME team. Form a multidisciplinary team with members representing various relevant functions and expertise. Define the FME scope. Clearly define the scope of the analysis, including the system, product, or process to be evaluated. Establish specific objectives for the FME, such as improving reliability, enhancing safety, or reducing downtime. Determine product or process functions. Identify the primary functions or components of the system, product, or process being analyzed. Determine failure modes of function. Determine potential failure modes for each function or component, considering all possible ways in which it could fail. Determine effects of the failure mode. Assess the potential effects or consequences of each identified failure mode on the system, product, or process. Consider both immediate and downstream effects, including safety hazards, production delays, environmental impact, customer dissatisfaction, etc. Assign severity ratings to each failure mode based on the severity of its potential effects. Use a predefined scale, example, 1 to 10, to rank the severity, with higher numbers indicating more severe consequences. Determine causes of the failure mode. Determine the root causes behind each failure mode. Assign occurrence ratings to estimate the likelihood of each failure mode occurring. Determine controls. Identify existing or potential detection methods for each failure mode, including inspections, tests, monitoring systems, etc. Assign detection ratings to evaluate the effectiveness of existing detection methods in identifying the failure mode before it causes harm. Calculate and assess risk. Calculate the risk priority number, RPN, for each failure mode by multiplying severity, occurrence, and detection ratings. RPN helps to prioritize which failure modes to address first based on their overall risk levels. Develop and drive action plan. Develop appropriate strategies to reduce severity, occurrence, or improve detection for each prioritized failure mode. Implement the selected actions to reduce or eliminate the identified risks. Establish monitoring mechanisms to track the effectiveness of implemented actions and verify risk reduction. By following these steps, organizations can systematically identify and mitigate potential failure modes, improve reliability, and enhance overall performance. This is a FME sheet. In this sheet, we can see the first column represent process description. The second column represent failure modes at each process step. The third column represents consequences of each identified failure mode on the process. In fourth column, assign severity ratings to each failure mode based on the severity of its potential effects. In fifth column, the root causes behind each failure mode is identified. In next column, assign occurrence ratings. In seventh column, determine controls. Next, assign detection ratings. Next, calculate the risk priority number, RPN, for each failure mode by multiplying severity, occurrence, and detection ratings. RPN helps to prioritize which failure modes to address first based on their overall risk levels. We can also use Pareto chart to identify what items to address first. This is FME severity rating criteria to rank the severity of effect. Higher numbers indicating more severe consequences. This is FME occurrence rating criteria to rank the likelihood of occurrence. Higher number representing the higher seriousness or risk. Detection is usually rated on a scale from 1 to 10, where 1 means the control is absolutely certain to detect the problem and 10 means the control is certain not to detect the problem or no control exists. Risk priority number, RPN, is the product of the severity, occurrence, and detection scores. Now let's understand with an example. In a FME risk assessment sheet, casting attach torque is the process being analyzed. The potential failure modes are over torque, under torque, and cross thread for this function. Potential effects of over torque is casting fracture, and potential effects of under torque and cross thread is casting separation. Severity ratings to each failure mode based on the severity rating criteria is 10, 9 and 9 respectively. The potential cause behind casting fracture due to over torque and casting separation due to under torque is torque wrench not controlled, and the potential cause found behind casting separation is no threading in bolt thread. Occurrence rating for over torque is 4 as per occurrence rating criteria. Use of DC torque wrench, linked to OMS, is identified as a current control for over torque. Detection rating for this particular control is 3. Here risk priority number, RPN, is 120. Addition of torque alarm and calibration at startup is the recommended action taken to reduce the severity, occurrence and detection for the over torque. By implement the selected action, RPN number is reduced to 20. By following these steps, organizations can systematically identify and mitigate potential failure modes, improve reliability, and enhance overall performance. Thank you for listening.